In this video, we're going to be looking at how we can implement stop ladders within the VectorBT PRO framework. So how we can scale out of a position once we've already entered it. For example, let's say we take a Bitcoin position at roughly this level, and we want to take half of our profit at this level and the other half at this level. Or if we hit this level, then we want to take 20% off the table. There are infinite variations of this position management strategy, and all are possible within the VectorBT framework with a bit of elbow grease. I'm going to assume that you already have a license for VectorBT PRO and that you already have your installation set up. I'm using the version released on the 1st of March 2025. So if you're struggling with this tutorial, if something's not up to date, make sure you've got the right version. This notebook is available in the GitHub repo, which I'll link in the description if you just want to follow along and you don't want to type up the whole thing line by line. So we start off with a few imports here, nothing special. Importing VectorBT PRO as VBT, NumPy, Pandas, and Number. Those are the three libraries that you're going to really rely on when it comes to VectorBT PRO. It's basically what the whole of the ecosystem is built on. As far as a data source, I'm using fake data here. So this is created using geometric Brownian motion. So just a method for creating false open, high, low, close data. I'm doing that so that there are no issues with licensing with the data and so that everyone can have the exact same data, because we're setting a seed value here. So the data generated for each of these fake symbols is going to be exactly the same each time. And that way, when you follow along the tutorial, it'll be the same for you. So we're creating this fake data and we can plot it out here. Obviously, this is not real Bitcoin data. So we've got BTC, we've got ETH, and we've got XRP. Those are our three different symbols which we're running this strategy on. Now, VectorBT has some built-in methods for doing basic laddering techniques. So, for example, if I just want to set a few different levels, say 10%, 20%, 30%, and I want those levels to take the same amount of profit at each point. So I have 5 points, let's say this is 10%, 20%, up to 50%. And I just want to take an equal amount of my initial position out at each of those levels. That's very simple to do here. So I'll make this even more simple and then build it up so we can see what's going on. So we just have a simple from signals, which is the main simulation function that you'll use in VectorBT PRO. All I'm doing here is I'm taking the symbol wrapper. So that looks like this. So if I just grab and show you what this looks like, these are my entry signals. So I'm taking each symbol as a column and then each timestamp on the index here. This is the format with which you'll want to feed in your entries. So if you wanted to make this based on some kind of indicator, you'd want an array like this of true and false values, and true is going to mean enter. So if we scroll down, the next thing I do here is I just set the value of the first row here to be true. So if I print out this value of entries, you'll see just the first line is true, everything else is false. What this accomplishes for us is it just gets us into a position immediately on the first tick, as in this video, we're much more concerned about position management versus what indicators we're combining to get into a position. And then we feed that into from signals here as entries, which will default to long entries, just as a long position, along with our price data, which we can just plug in, the one that we got earlier. And as far as the actual take profit ladder, it's quite simple. So you just say stop ladder is equal to uniform. As I hinted at earlier, the simplest version of this is going to be taking out an equal amount of the position at each individual point. And then you simply set TP stop to some array, or a list in this case, of the different values. In this case, each one of these is going to equate to a percentage take profit. So 0.1 is going to be equal to 10%, 0.2 is going to be equal to 20%, so on and so forth until we hit 50% if there's still enough of a position there. Let's run that. Now, on first run, this PF from signals does take quite a while. It can take 30 seconds to a minute to compile the first time because it's using number behind the scenes and it has to compile a lot of functions. If you're just changing values from here, most of the time you won't have to recompile and it'll be much quicker. So let's plot out what happens when I run this so you can see what's happening. So down here we've got pf.trades.plot and we haven't set that up yet, so I'll just do that. And you can see we've got a 20% take profit here at a value of 10%. So you can see the return value there is 10%. The next leg up, the return's 20% and it's taking the same size. And then up here it's 30%, it's taking the same size, 40%. And it looks like we never hit 50% above our base price. So we're still holding about a fifth of our initial position at the end because that particular leg of the take profit never hit. If we look at Bitcoin, we can see it's done the same sort of thing. It's taken a 10%, 20%, 30%, and then we've evidently got about 40% of our position left at the end. Now, to make this more interesting, you can pass in multiple stop ladders at the same time and do a bit of optimization or seeing which one performs the best. We do this with VBT.param, like so, wherein we can set multiple take profit ladders. So if I make this a 2D array and I make another ladder like say 0.2, 0.28 and 0.3, let's say, and give that a run. Looks like it had to recompile there as I made a rather significant change adding this VBT.param. Let's go take a look at the output here. So if we do pf.sharp ratio, we've got two different stop ladders now. So we've got list 0 and list 1, and we've got the sharp ratios for each of these combinations. So this take profit ladder and this take profit ladder with all the three different symbols that we implemented. Before, you'll remember I had this argument called keys here, and that was just to give us a more human readable output here. So ladder 1 and ladder 2, just to make this easier to read. And so you can tell which one's which when you're doing your analysis later on. And if you wanted to plot those out, all you would have to do is make sure you're indexing into the right column. So we go ladder 1 and then the symbol that you want. So just read this left to right. So ladder 1, we paste that into here, and then the symbol that you want. As we can see, this is exactly the same as it was before. Let's check out ladder 2. And it looks like this. So we've got about a third of our position being exited here, about a third here at 28%, and then the rest is kept. So if I remember correctly, yeah, we had 20%, 28%, and 30%. And stop ladder has been set to uniform this entire time. So it's going to take about a third off the table at each individual point. Now for variety, we can change this to weighted. which uses this price formula here. So I've just lifted this directly from the code. So price is the current price that the stop is executing at. So we're executing at, let's say, 20% above what we bought at. The previous price is wherever the previous stop executed, or the initial buying price if there wasn't a previous stop. This last price here is the price of the last stop in our array. So maybe like 30% or 50% here. And then initial price is the initial price that the position bought in at. This is the formula that it uses underneath the surface. If I change this to weighted, you'll see how that works. So I'll make a change here to make this a bit more obvious. I'll set this 0.5 and then 0.15 and 0.3, and you'll see the difference here. Ladder 1. So initially, we're going to take one of our take profits off the table at 5%. It looks like about 10% of the position. The next one was set for 15%. And the difference between 15% and 5% is twice the difference between 5% and 0%. Because, 10 is twice 5. Therefore, we're taking about 20% off the table at this value here. And then our next one was set to 30%. So again, the difference between this point and this point is 15%, which is 3 times the difference between this point and this point, which is why the exit size is about 3 times. I forgot to mention that this fraction here is multiplied by whatever the initial position was. So we take this exit fraction, which is calculated on these values I mentioned earlier, and we multiply that by whatever our initial size was, which is roughly 1 unit in this particular simulation. Easy way of thinking about it is just look at the gaps between the different values. So the gap between this point and this point is about 1.5 times the size of the gap between this point and this point, which means the exit size is going to be about 1.5 times this value. So here the size is 0.196 and here it's 0.294. Hope that makes sense. If not, have a play around with it. I don't tend to use this weighted parameter. Later on, I'll show you how to make something completely custom so that you can create your own formula for however you want to take your take profits and stop losses. We also have this idea of adapted ladders, again built in directly to the library. We have AdaptedUniform and AdaptedWeighted. The idea behind these is that it's all well and good having this stop loss that takes a certain chunk of your initial position out at each individual step, or a take profit, but what happens when you have a stop on the opposite side that reduces your position? So let's say you've got 5 take profits that take profit in each individual level. What happens if after your first 2 take profits, you have one of your stops trigger and that lowers your position? It's going to mess with the take profit laddering if you get back up to that level, in that you won't have enough of a position to take profit on those remaining 3 levels. So if we took, say, 20% here, 20% here, price goes down to this point, we take another 20% off the table. We have 3 more 20% take profits to hit. We just don't have enough of a size to hit those. That's kind of the problem that this is trying to remedy. So it uses these formulas for the exit fractions, and it multiplies it by the current position. So not by the initial position that we took, by the current position that we still hold. So in this case, for AdaptedUniform, it's going to be 1 divided by however many steps there are in your ladder. So that's this last step plus 1, minus the previous step. So if there are 5 steps, it's going to be 1 divided by 5 minus 0 for the first one. So it's going to take a fifth, which is 20%. And then on the next one, step is going to be slightly bigger. So it's going to be 1 divided by 4. So it's going to take, again, 20% because you have a position size now of 80%. You've taken 20% profit. It's going to take a quarter of that. and then a third, and then a half, and then the whole thing. So if you have no other signals that happen during that range, something like AdaptedUniform or AdaptedWeighted behave exactly like the non-adapted variants. That was a lot of me talking, so let's just run this example. I think I've already run it here, so I can show you what's happening. I'll have to run it again. We can see that it hits a stop loss here, takes about 20% off the table, another 20% off the table at this point. So remember, we're using AdaptedWeighted, which is going to use this formula here. So as the gaps between the stops get wider, so does the fraction of our current position that we take out. So just looking at this, what we'd expect is the amount that it takes out at this point should be the same as what it takes out at this point. It should take out less at this point if it hits it, and then more at this point, because the gap between here and here is less than the gap between here and here. The take profit should behave pretty much the same as the uniform one, because they're all the same distance apart. Let's see what that actually looks like. So 20%, and then another 20%, all well and good. Now we have that situation I talked about where we have a take profit interrupting our stop loss ladder. And that's taking 0.12. So if we think about it, we've taken off 0.2 and 0.2. Our current position is about 0.6. It's taken out 0.12, which is a fifth of the current position. And so it's basically behaving as if we not had all this happen to us, and we just entered a position here of size 0.6. That's essentially what it's doing. And then it takes out another 0.12 here, because these are the same distance apart. This is a 10% return. This is a 20% return. Down here, it's going to take another chunk, although you'll notice, again, like I mentioned, it's significantly less than what you'd expect. I can't do the math in my head anymore. The numbers have got too complicated. But when we go back up here, it takes another yet even lower chunk. So you can see this value that it takes, the size amount, is lower than the size it takes at this amount, because that position has been taken away by this stop loss that interrupts the take profit ladder. I will mention that these functions here are independent of one another. So this previous price here, for the take profits, only takes into account the previous take profit price, and for the stop loss, it only does the same for the stop loss price. Again, I don't use these adapted functions that much, so I'm not going to spend too much time on them, but feel free to play around with this example and the different values if you're interested in using it for yourself. It's worth noting this little line here, this adjust func NB line. I had it originally in this one, but I removed it for simplicity. What this allows you to do is it allows you to insert a function into the signal logic, or the position management logic, to change the values of the stop losses and the take profits, as well as a few other things, dynamically, rather than having to set them like this and just give them as an array into the function. And we do that by providing a regular Python function that is compiled with number, and just pass it in as the argument here. So I'll run this and I'll quickly show you. For now, I just have a very simple function here. It's just called adjust func print. It has the ngit decorator, so it's compiled with number. And all it's doing is getting the information for the current take profit from the simulation context. So when you provide this function, its first argument needs to be this C value. I think you can call it whatever you want, but the first argument is going to be this thing called the simulation context, which holds this array called last TP info. And this array contains a named tuple called TP underscore stop, or at least that's what I've called it. And that contains a bunch of information for the current column. So remember, when I showed you before, we had 6 different combinations, right? We had ladder 1 with the 3 symbols and ladder 2 with the 3 symbols. So in this case, it's doing 6 different simulations, essentially 6 different backtests. And each backtest is going to have its own information so that the simulation can keep track of what's happening with the take profits. That's what this does here. So we select the take profit for this particular simulation, whichever simulation is happening now, and we print it out. And all the effect that that has is it just prints out this stuff here, which if you know how to read it is very helpful for debugging your system. Each of these values in this name tuple all mean something. In particular, you can look up this. So vbt.pf_enums.tp_info_fields. Or you can just look up this in the documentation and you'll find it. But it tells you what's happening in each of these items. So we have this init index, which is wherever the position was entered, the init price, the price at which the position was entered. Most of these are relatively straightforward. We have this ladder value, which tells the system whether we've set it to uniform or AdaptedUniform or weighted, etc. Step, which is the step of the ladder that we're currently on. And step index, which is the row in our data at which the step was last triggered. That's what's going on here. It's very handy for debugging what's going on later on with your system, especially if you do something like restricting it to just printing out one of them. So, you know, if c.call is equal to 2, you know, that'll give you only the printout for a particular backtest. You'll have to do a bit of investigation to figure out which one corresponds to column 2, but you get the idea. Now, the last thing I want to show you is the most powerful version of this. We've currently just been using the inbuilt parameters to from signals, and you can do a lot with this. You can do more than what I've shown you here. There's lots of cool things you can do with these vbt.params and broadcasting, etc., different parameters for from signals. But the most powerful version, the most flexible version, is going to come from using dynamic mode. So if we scroll down a bit, remember we had that adjust func? Well, we can make these much more interesting by providing a few parameters here. And instead of setting something like a particular stop ladder in here, just provide arguments to this function, and we're going to run our own stop loss or take profit management techniques, our own algorithm that we created, rather than relying on one of the inbuilt ones. To do this, you just set take profit to dynamic, which basically means ignore this TD stop argument, ignore that, or the or TP stop rather, ignore that argument, and instead activate the ladder. So when we hit a take profit, we still have a position. That step in the ladder context still increments. A lot of the machinery behind the system is still going for a take profit ladder, but it doesn't hold a hand. It doesn't do a lot of things for us, which is why we need this adjust func argument. And so instead of the simple one that I provided earlier, we have a slightly more complex one, but it's relatively simple when you break it down. So we take in a few arguments, just like a regular function here, you know, price multiplier, size multiplier, move SL step, and move SL level. Now, to make life simple, let's comment this out, and we'll go through this kind of line by line as to what's happening. So TP stop, again, all we're doing here is we're getting the information on the current state of the take profit for this particular column. So where is the stop set? What level of the take profit ladder are we in? When was the take profit ladder last hit? What was the last step? When did that happen? How much are we going to exit at the next step? All of that information is contained within here. That's what we're grabbing from the simulation context, which is this C value here. Then we have an if statement. So if the exit size, so if the amount with which we're going to exit the next take profit is NaN, so it's undefined, and this value of step is greater than -1, then do what's in here. Now, basically what this does is we only want to run this after the previous take profit has been hit. And what happens when the previous level of the take profit has been hit is that this gets set to NaN, and with this, we're just making sure that a take profit ladder's actually defined. If we exit out of a position completely, 100%, we have no size left, this step value in the TP stop will get set to -1, which will mean that, we're not continually telling the simulation to exit at certain levels when we don't even have a position. That's broadly what these checks are doing here. There might be some more edge cases, but this works for our purposes. And then all we have to do to actually set a particular take profit is change these values. So exit size type, stop, and delta format. These are the main ones to focus on. Again, there are probably more that you can change in here. And you can have a look at those particular values. So price, size type, exit type, order type. All these different values, but these ones work for our purposes. So the exit size is going to be the actual amount of the position that we're exiting. I'm setting that to our size multiplier parameter, multiplied by the step of the ladder that we're on. So step starts from 0, so I'm adding 1 to it to get based on 1. So on step 1, it's going to sell size multiplier multiplied by the initial position. So if we have an initial position of 1, our size multiplier is 0.1. Then we're going to sell 10% on the first level, 20% on the second level, 30% on the third level, etc. That's all this little thing does. This exit size type, again, you can look inside this pf.enums.size type. If we do vbt.pdia, vbt.pf enums.size type, you can see there's a bunch of different values here. So amount, that means this is going to be the actual amount of the asset. So if we have, say, 1 share and we want to sell 0.2 shares, it's telling VectorBT what this number means, and it's telling it that it's the actual amount. So as opposed to amount, we could have percent, for example. And if I set that to percent, rather than saying this whole thing, we could probably just get rid of this if I set it to percent. And in that case, it would be, 0.1 times a step, which is, say, 1 in this case, which leaves it at 0.1, i.e. sell 10%. There's a few other values you can try. You can try target, for example. So it's going to try and buy or sell a specific amount. Not sure if that would work, given that it's only a take profit, but feel free to experiment. In our case, I've chosen just amount here. And then there's the actual stop, which this is the price that we're actually going to exit at. So I've just used the price multiplier, again, another one of our inputs, multiplied by the step of the ladder that we're on. And in this case, I've set it as percent. So again, if this is 0.1, this price multiplier here, and we're on the first step of the ladder, our first take profit is going to be 10% above the initial price, and the size is going to be 10% of our position. That's all that's going on in here. I'll try and run this just straight up, just so you can get an idea without me talking all the time so much. We'll comment those out, run this, and run this. Of course, we need to comment out this as well. Otherwise, it's going to expect more arguments. So let's have a look at those results. If I plot these out, you can see basically every 5% increments, this is 5% above, the return is 5% there. We're selling 5% of the position. And at this point, we're 10% above, so we're now selling 10% of the position. So it's 5% times 2, which is a step on the ladder. So it's 10%, then 15%, then 20%, 25%, 30%. It looks like we don't have enough to sell 30% there, so it's just selling everything that it has. But you get the idea. And although that did take 25 seconds to calculate the first time, if I just change one of these values, change this to 0.8, if I just do that, you can see it's extremely quick to calculate everything out the second time, and that's because it's all compiled. If you want that to work in a Jupyter notebook, make sure this adjust func is in a separate cell. Otherwise, it probably won't work and it'll have to recompile every single time. So let's see what that looks like now. you can see it's taking a roughly 8% stake at that point, then 16%, then 24%, 32%, and then whatever it's got left. So I hope you can see how this can be quite powerful in that we can have this custom function that we can provide parameters to, which essentially creates our own algorithm for putting those stops in and how we manage our positions once we're in the position. Now, the second half of this function, which I'll show you, basically, once we get to a certain point, so once we've, say, taken 2 of our profits, once we've gotten to some number of steps, basically, of profit, so whatever step this is on the ladder, so after the first take profit, the second take profit, etc., at a certain point, then put in our stop loss. That's essentially what this does. So we're using all the same parameters, except we're just getting it from this SL stop, this last SL info, almost exactly the same as the last TP info. And what I'm doing is I'm saying sell 100% at this specific level, this move SL level, which I'm providing up here. If we plug some values in, we'll see how that works. Uncomment these. It'll have to recompile now because I've changed this function. Every time you make changes to this adjust func, the from signals will have to recompile. Not really avoidable, so ideally you want to set this up in a way that you're just editing these parameters rather than changing this function all the time, especially when you're doing large amounts of backtests. Cool, so let's see what happens here. So I've got this level set to 2, and I've got it set to minus 5%, basically. So what this will do is, after the second take profit level has been hit, so in this function, when this stop level is equal to 2, in this case, so when it hits the first one, it'll go from 0 to 1. When it hits the second one, it'll go from 1 to 2. When it's at that level, set the stop loss to minus 5%. We can see that in actuality, it goes on to hit 2 more take profits. We've still got some kind of position in the market at this point, and once it hits a return of negative 5%, it cuts our losses and exits. So a common thing to do in backtesting or trading in general is once you've reached a certain level of profit, move to a break-even level. That's very easy to implement with this system. So you can see here we're just exiting at break even. We've hit a bunch of these take profits. We had no stop loss this entire time. And then once we hit this one, the stop loss gets implemented and we hit it here. Hope you can see how valuable this can be in terms of testing out cool position strategies. I made this even more interesting and complicated here with instead of just providing, like just messing about and tweaking these one by one, that's a little bit tedious by hand. We really want to make VectorBT do this for us. So broadly speaking, this function is exactly the same. So all of this logic here is exactly the same. Down here, you'll see this looks slightly different in that I've passed everything to this broadcast named args. And instead of just providing these as like a raw number, like 0.05, we've got this vbt.rep here. The rep stands for replace, if you're wondering what that is. And so what this is going to do by the magic of VectorBT is it's going to take all of these combinations. It's going to take the Cartesian product of them. So it's going to take a price multiplier of 5 and 5 and 1 and 0.5. And then it's going to take 0.5, 0.5, 1 and 0, 0.5, 0.5, 1 and 1. It's going to take every possible combination of these parameters and backtest that for us. And then we can look at things like the total return, the Sharpe ratio, whatever it is you're interested in. And we can see if certain ranges of values produce desirable statistics and test that for different date ranges, etc. That's what this whole setup does. It calculates the Cartesian product of all of these and feeds them in to the adjust func by replacing these strings with the broadcasted values. It might make sense if I show you the output for this. So here is the total return sorted in descending order. So you can see we've got a price multiplier of 0.5, a size multiplier of 0.2, the step value of 3, and the move SL level of 0. And then this is one particular parameter combination, and that gives a total return of 33% over the time period. And then you've got the next one here with a value of 2. And then next, yeah, you can see it's just changing one parameter each time. And we've got 432 different backtests there. If I run this again, you can see how quickly that ran. So I could change this to 0.17, for example. You can see that's running 400 different backtests. And that was super quick, right? So once you have things compiled, these backtests do actually run incredibly quickly, especially considering, like I said, we just ran 400 backtests just like that. And again, if you want to look at some specific value, you can just follow these from left to right. So, we have a price multiplier of 0.1, 0.14, and minus 0.05. You can enter these values in here. So 0.1, 0.1, that's a 4, and minus 0.05 on ETH, or our fake Ethereum data. Now, obviously, this is overfitted to an incredible degree. You'll have to do your own cross-validation on this and robustness checking. But I hope you can see how powerful this is. So those are the changes that we made here on this front. All we did basically is we passed a list of arguments to this vbt.param, and we set them, named them as we did here. And behind the scenes, from signals going to morph these lists of parameters into some two-dimensional vector that it's going to iterate on in a way to save memory. Let's not worry about the implementation details too much. But we do have to worry about them a little bit. We have to use this function here, this select NB function. So instead of just passing this value directly into here, so this stop like we did before, instead what I'm doing is I'm selecting a specific value. So because we're doing this whole Cartesian product, this is actually going to be an array. So I'll just print it out, and you can see, kind of what's happening. It'll not be super obvious, but you'll see that something's changed at least. I'll set that running while I talk. So for all of these values, it's not going to return just a single integer. It's going to return some kind of two-dimensional array. Now, this section down here, this assumes that we've, added some kind of float or an integer or something like that. So if you just try and pass a 2D array to, say, this formula here, it's going to get really confused. And so we rely on this select NB function. It uses the simulation context. So whichever particular, it goes bar by bar. So, for the first simulation, the first set of parameters in the first symbol, that's going to be a particular column number. Let's call it column number 0. And then each bar is going to be a row in our data. It's going to extract that information from this simulation context and then index into the correct value of price multiplier to give us the price multiplier at that specific time for that specific column. Hopefully that makes sense. If not, just play around with this a little bit and copy it and see what you can come up with. Now, I may have crashed my system here, but let's just try and stop this from running. Okay, killed the kernel, that's fine, I'm done anyway. But you can see what's happening is that when I printed out this value of price multiplier, it's printing out this massive array here. And I mean, my guess would be that this contains the same amount of elements as the backtest that we're doing. And each one of these corresponds to a column. So the very first test we do, we have 0.5, the second test, so on and so forth. And then eventually we run out of all the other parameter combinations. So we go to 0.1 and then we do all those tests, and we go to 0.17 and we do all those tests. And it would be the same for any of these 4 values that you print out. That's what's going on, and luckily we don't have to worry about that. We can just tell VectorBT, pick the correct value for this particular backtest, and then just shove that in our initial logic. And that gives us, this lovely parameter optimization without doing a lot of work on our behalf. So we had the simplified version above, where we just input our own numbers. And then this version down here, where we could input, a range of values, it'll do the Cartesian product, and even better, it'll calculate all of those in roughly the same amount of time. So I hope that was a nice introduction to stop ladders in VectorBT. I'll be making a few more videos on VectorBT Pro. Let me know if you like them, and I'll see you next time.